All right, let's get started. Last class, what we did was governing equation for the two-body relative motion. We developed this, and it read as r double dot plus mu over r cube vector r is equal to 0. Where this r is the relative position of the smaller body with respect to larger body. Okay. Mu is the gravitational parameter. Moving forward, we'll operate under these conditions or assumptions. One, M1 is much larger than M2. Two, gravitation is the only external force acting on the system. Three, M1 is spherically homogeneous. Okay. So we said if we look at this is a second order differential equation, right? To solve this, you need 6 constants of motion. What we are going to do is we're going to develop, or let's say develop 10 constants of motion. Okay. So the first set is angular momentum. So this is how your angular momentum is defined, right? Angular momentum. So how do you read this? h2 bar 1, the angular momentum of 2 with respect to 1, okay? So is equal to r crossed with m2 r dot, okay? So this is angular momentum is the angular momentum of body mass m2 with respect to m1, okay? That's weight h vector, yes. H vector 2/1. So angular momentum of body 2 with respect to 1, okay? Let's define small h as h to 1 over m2. This one with respect to WRT is with respect to this one, double dot, huh? Mu, relative position of smaller body with respect to larger body, huh? This one, R relative, huh? Where? So what we do is we define something called h, small h, okay? Lowercase h. This is the specific angular momentum, okay? Angular momentum per unit mass. So we define this. So once we define this, you can write h, this small h, as what? R crossed with r dot, right? If you define specific angular momentum as h2 bar 1 over m2, you can write r crossed with m2 r dot, or sorry, r crossed with r dot, okay? This is the specific angular momentum. Now, dh over dt is equal to r crossed with r double dot minus r dot crossed with r dot. Okay? So you agree with this one? The vector crossed with itself, 0, and we also know minus mu over r cube r, right? Substitute above in A. Let's call this A. So what you're going to get is dH over dt is equal to r crossed with minus mu over r cube r. Okay, so this is minus mu over r cube r crossed with r. So this goes to again 0. Therefore, dH implying dH over dt is equal to 0. Again, this is a very important result. What it says is angular momentum of the orbiting body in a two-body system is conserved. This is conservation of angular momentum. So this is, see, we said we'll develop 10 constants of motion. So what you have done here is you've developed 3 constants of motion. Can you tell me how you have developed 3 constants of motion? Essentially what you're saying is this is 0, or conservation of angular momentum is h, which is equal to r dot is equal to constant, not 0. dH by dt is 0. The derivative of a constant is 0, right? The derivative of a constant is 0, but the constant, this is constant. Okay. Is that right? Everyone? Do you see it? Is this all right? Everyone? Miss Andover? You guys, you don't have to copy. I would strongly recommend not to take down notes, because otherwise you're not going to follow, and middle of the semester you'll be lost. Just take a picture and write. This will take like 5-10 minutes to take down the notes, or just go through the lecture again and make your notes if you really want to make your notes. Otherwise you're not going to follow. What is the point of taking down notes? You don't have to review the lecture. You can take down a picture and write down the notes again. If you see, if you're not following, now tell me why this is 0. Huh? Tell me why this is 0. Huh? Why? Huh? Hmm? Mm-hmm. Why is it 0? I'm asking why is it 0? What makes it 0? Huh? Huh? The definition of cross product is there's a sine theta there, right? In the definition of cross product, the vector into sine theta. The angle between the same vector is what? 0. So the sine theta term goes to 0, and that is the reason it is 0. All right. So do you agree with this? Mm-hmm. Huh? It is r dot. It's not r double dot, and that's what you guys have to pay a little more attention. And if you're taking down notes, it's going to be, you're not going to pay attention, and later it's going to be difficult. Okay. Anyways, so this is what we have proved. Okay. So why is this going to lead you with 3 constants? This quantity is a vector quantity. H is a vector quantity, right? So you have 3 scalar constants. Got it? Hmm? H is a vector. Who said the magnitude of it is constant? That's what. Where did the magnitude surface? Where did the magnitude surface? Here we have proved the vector itself is constant, right? We did not prove the magnitude is constant. You see this? So this means the vector itself is constant. So what happens is, so if you want to get the 3 constants also, you can think about it like this. If you want to get an expression from this for r, how would you do it? You would integrate this once, right? R crossed with r to get an expression for r, and you'll end up with 3 constant of integration. Okay. So this is the first 3 constants. All right. Now, please follow this part of the discussion. What we did here was just, it's more of a showing that angular velocity is conserved or constant. So you could do it as a derivation, but this one is much more important with respect to visualization. So you have, let's say, the body, right? And we have this, okay? So you have, let's say, this is the position vector. Okay. Now this is the body mass m1, and here you have m2. This would be your r, correct? This would be your r dot. Okay. If you take the cross product of this, you are going to get, if you're going to take the cross product of this, you're going to get h. Okay. H is this. The reason this is important is visualize this first. Okay. So you have the particle is, let me pull up something, see if I let me. All right, this might help explain. All right, is this visible? Okay. Better? Okay. So what is R here? This distance, right? And this is also R, right? At another time instance. What is the velocity? Velocity is in this, right? Now we said R dot V. This is V. R dot is V. R crossed with V is the angular momentum. So if you take this and this, imagine if you have R crossed V, where would H be, in what direction H? So you have R and you have V. Think about this. It would be in this direction. It's always in this direction, right? So you have, see, H is my thumb, R crossed with V, R, V, R crossed with V. H is always in this direction, right? So what? Right. H is going up. Here it is, if you think about R in this plane, V in this plane, then H is coming through you. Got it? Right. Here it is, here imagine, It is. Right. But that thing is kind of oblique. The plane, it's not really on the plane. It's not shown to be on the plane. You see what I'm saying? So it is going up, or it's coming towards you. Okay? So H is coming towards you, right? Or H is going up. This H has to be constant. Why? Huh? We just showed it because we just proved to, right, we just proved that this has to be constant. And when we say this has to be constant, it has to be constant in direction as well as magnitude, right? See, if this direction has to be constant, direction and magnitude has to be constant, this has to be, R and V have always got to be in the same plane, right? If it changes, then this will change. Okay. This proves, see, the H constant proves that orbits are always in a single plane. R and V are always in a single plane. How do you define a plane? How do you define, how do you identify a plane? The perpendicular to the plane identifies the plane. Okay? So this H is always perpendicular to the orbital plane. Do you see that? Are you able to visualize that? Because H is constant, the orbit will always have to be a plane. And this H is always perpendicular to the plane. Okay? So this plane, it will always keep rotating in that plane, as long as it is under the influence of only gravitational force. Something else, it will change. If you fire a thruster, that is another external influence, correct? So it will change the plane. As long as we are discussing Keplerian motion. What do you mean different times? That's the plane. What do you mean? What do you mean by different kinds of plane? I did not. See, for example, this, you think about this plane. How would you identify this plane? By this vector. This vector will always identify this plane. If I change this vector, this plane itself will change. You cannot really define a plane, right? So this is how you define a plane or identify a plane. So you can say 1, 2, 3 points, right? That is the other definition of a plane. 3 non-collinear points. But it can be anything, right? So if you generally want to discuss this plane, you can say we'll use this perpendicular to that plane. No matter where you go, how far you go, this perpendicular will always correspond to this plane. Not landmark, but it's identification of that plane. Identification is a simple word, right? So if you, for example, if you talk about this plane, it is this perpendicular. No matter how far you go, it will always be that plane. Okay? Most of our discussions, okay, are going to be, you have to visualize the orbital plane from the top view. So if I draw this, this should be absolute top view of the orbit. Understand? This will be your, we'll discuss this. If I say F, this is where the central body is. And this is the orbital motion direction. If I don't give you an orbiting body here, it shouldn't bother you, because an orbit will not exist without an orbiting body. See, orbits are not out there. You understand that, right? It's just all free space. Only when something starts orbiting, we abstract that or we visualize that as an orbiting plane. So when this comes into picture, you should immediately grasp that there's an orbiting body in this plane. Okay? And this distance would be the position vector at any time instance t. Okay? So let's do, what time do we have? We have 10 more minutes. Okay. If you have this motion, and let's say you have the central body here, all right? This is R. This is the motion. This is the central body. You have, this is the position of the orbiting body 1, let's say 1 and 2. 1 is the position of the orbiting body at time t, okay? And 2 is the position of the orbiting body at t plus del dt. This would be your, so this would be your velocity vector, correct? So this velocity vector will always have a VR component. So in fact, you can take this as the velocity vector, right? So this V velocity component, there is a VR, and there is a component V perpendicular okay. Are you able to visualize this or not? This is VR and this is V perpendicular. Okay? Think about this. When you have a mass attached to a string and you're trying to rotate that mass, there is a component which is pulling this, which is making the string go away. That is this component. And then there is a component which will give a tangential motion. That is this component. All right? If you think about it, H is RV only. This component, only this component is going to contribute to the angular momentum. You agree? Why is the radial component not going to contribute to the angular momentum? There's a radial component and there's a tangential component. Mm-hmm. You think about this. If you split this, if the velocity, this component is in the same direction as this, the angle again is 0. That sine theta again will be 0. So the entire contribution is because of this. So we can write the magnitude of angular momentum is equal to R into that V perpendicular or V tangential. Okay. Now, here, just think about this triangle. Okay. This, and this. Okay. This is R t plus u t at time t. This is R t plus dt, and this is V into dt. Okay. What we want to figure out is dA by dt. Let me not discuss this now, but let me give you what we are going to talk about. You can get a heads up. Kepler's second law, which states equal areas in equal times. We'll prove this, but you just looked at this, correct? Yes.
Can you point out where dt is on that order?
V dt is from this point to this point. See, this point, this is a distance, correct? Right? So distance, how do you get this distance? Velocity into time. So between this and this, what is the time elapsed? Dt is the time elapsed. And what is the velocity? V is the velocity. So if you want this distance for very small sectors, it will be straight lines. So if you think about that sector, straight line, this is that distance, V dt. Now, this is Kepler's second law. And this is, we proved this, right? This is a direct consequence of that. You have to try and appreciate this and that. The reason I'm saying is, this we proved mathematically. We arrived at this mathematically. This was shown, or observations were made to prove this, right? When what it says is planets sweep out equal areas in equal times. So you think about this. Is Earth moving faster here or here? Think about it. Equal areas and equal times. Anybody else? Why? To make up for that, see, how do you calculate? Think about this as a triangle, right? So what is the area of a triangle? Huh? Half base times height, right? So the height is, here the height is much bigger than this height, correct? So it has to cover much more base here in the same amount of time as compared to this, because the height is compensating here. It doesn't have to cover as much base. You understand? So here it has to, base is, yeah, half base into height. Base would be, yes. So base would be V dt. This would be the base. Height would be this RT. So if height is more, it has to cover the same amount of area, correct? So if here height is pretty much this, right? If this is the base, this would be our height. Here this height is much less compared to this height. So to cover for that extra base, it has to move much faster here when it is closer. And this also, this and this actually mean the same thing. That angular momentum is conserved and planets sweep out equal areas in equal times is the same thing. And we'll see why it is the same thing in next class.